Welcome everyone. We are up and running. Not anyone in here live right now. I am looking for questions from lessons 8.1, 8.2, or 8.3. Let me share my screen. You can certainly contact me, as you know, by text message. So let's do the sharing. Okay, you should be seeing my screen. I happen to have up the 8.3 assignment, but anyone, either 8.1 or 8.2 or 8.3, I'm going to create a slide here so that I can remind you of a couple things. Get my keyboard moved. So we are taking questions on any one of those three assignments that you had for last time. You can text me. Since nobody's directly online, I'm assuming some of you might want to use that route to contact me. Okay. I think we got one here. Lesson 8.2, number 29. Thank you, Rhonda. 8.2, number 29. Okay. So we're going to start with this request, 8.2, number 29. Let me get there. Okay, 29. Oh, it's one of those proportion problems. Okay. So I don't know if we have the time here, but I'll try to sketch this out. And we've got the part, this is PQ. And on number 29, we're given AP is 3. PC is 4. BQ is 6. And you're supposed to find BC. So I'm going to call that X. So BC goes all the way kind of the length of that arrow, this whole side, and that's what you want to find, okay? So you could, Rhonda, set up your proportion like this. You've got, remember, you've got two, you've got the little triangle, triangle CQ, and that is similar to triangle CAB. So the little triangle similar to the big. So when we set up our proportion, we're going to want to go little to big or big to little. So I'm going to say left side of little is to left side of big as right side of little is to right side of big. Now, I didn't show this to you, but if the whole side, if CB is X and just this part of it is 6, then doesn't this part here have to be X minus 6? I did the wrong way, didn't I? So let's just go back. Left side of little is to left side of big. Right side of little is, so I've got to reverse that. Okay, so it's a good thing I drew it out. So X minus 6, the left side, the right side of the little is to the right side of the big. Now we can cross multiply. 4 times X equals 7 times X minus 6 Okay, I'm not sure. I just got another message and it doesn't look like it's any different. Okay, well, anyway, continue to the right side, 7 times x minus 7 times 6. Now I would subtract 7. I want to get x alone. So let's subtract 7x from both sides. So we'd get negative 3x equals negative 42. And then to get rid of the negative 3, because it's being multiplied, we would divide both sides by negative 3. And x is equal to 14. And that should be it, because it asks us to find BC. Yeah, that's what we just found. Okay. All right, Michelle, thank you. Same lesson, 25 and 49. All right. So hopefully that took care of number 29 for you, Rhonda. So I'm going to go back. Let's do 25 next on 8.2. And then I got to remember 25 and 49. Okay, number 25 on 8.2. Which of the following triangles are similar? In order to find that out, we'd have to check out proportions. So let's just say, let's try A and B first. If A and B are similar, then what? Should we just left side of left side of left triangle is the left side of right triangle as what? Bottom of left triangle is to bottom of right triangle. And the question is that true? Well, if you multiply, let's see, 2 times that 3 point, so this would be 7.6. And if you do it the other way, you get 7.8. So that tells you these two are not similar. So then we could try, how about A and C? Let's see if those work. So left side of left triangle is to left side of right triangle as right side of left triangle. 3 is to right side of little triangle on the right. And if you cross multiply, this one works. So we have, I mean, I should keep checking, but I think I've done enough to show you. So in other words, how do you find out? By the way, what have I not tried yet? I haven't tried B and C, right? I mean, we've tried A, B, we've tried AC. The only one I think remaining is BC. And anyway, I'll let you check that, but AC definitely works, hopefully. So how do you find out if two triangles are similar? By checking if the sides really are proportional. Okay, Rhonda, you also asked about Michelle, you also asked about number 49 on this same assignment. So let me go there. Okay, 8.2, number 49. So we've got these lines, and you're supposed to find measure of angle BCD. I guess I better make a drawing here. So we've got a vertical line, we've got this one on an angle, and we have these. Let's get some letters in here. C, B and D, A and E, and this is 120 degrees right in here. And you're supposed to find the measure of angle BCD. BCD. So you're trying to find, let me change colors here. You're trying to find this angle up here. Okay? Well, we've got this idea of, let's see, how can we do this? If this one's 120, then by supplements, that angle BAE has to be 60, right? And BAC is 60. That means CBD is 60 because they're called corresponding angles. They're in the same places where the parallel lines meet. And this, where we told we have a perpendicular, yeah, this is perpendicular, so we know this is a right angle. That was given. So that means the only thing this angle could be here is 30. Why? Because the three angles of a triangle in triangle CD have to add up to 180. And we've got 60 and 90 already accounted for, leaving us with 30. So that would be number 49 on 8-2. All right, those are the three requests I've received so far. Are there any others? All just happen to be from lesson 8.2. That's fine. Okay, at the moment, not hearing any, I am going to move to the new assignment. And that would start here. And the title of our lesson, oh, we did get a, okay, I did get another request for 8.2, so I'm going to go back and do that. And we'll come back here. Okay, so let's make another slide here. And this is 8.2. Oh, 8.3, number 37. Got it. Okay, Rhonda. So this one I'll just show you. It's kind of a long, actually not a very hard calculation, but a lot of conversions to do because of the units. So on 8.3, number 37, we've got this motorcycle tire guaranteed for 20,000 miles. Okay. In 36, they told you about the tire's diameter being 26 inches. Okay. And it wants to know how many revolutions does the tire make in one mile. And then we're supposed to go further and say how many tire rotations are there in 20,000 miles. Well, in order to find how many tire rotations are made, we have to find out how much is one rotation. So we take the diameter of 26 and we plug it into our good old circumference formula. And well, here's the answer exactly. I know maybe not what you want to see, but 26 pi inches would be how far a wheel goes, that wheel goes when it makes one rotation. All right, so each rotation is that many inches. So now, how many of those inches are in 20,000 miles? So you notice I took 20,000, but that's miles. I've got to, what, convert that first of all to feet. And if you look at number 36, they showed you that there's 5,280 feet in each mile. So I had to multiply by that. And then that's in feet. I still have to change it to inches. So I also had to multiply it by 12. So now I've got on top how many inches there are in 20,000 miles. And then on the bottom, I've got how many inches there are in one rotation. So now we can finally divide. And you could go ahead and use a calculator. I'm not trying to impress you or anything here. I just wanted to show you without, if you use your pi key, you get all these digits. Of course, we want to round this off. So I would say 15,513,934. And if you go to the 100th, it would be what, 0.15? rotations. So that, I mean, the calculation wasn't very hard. To change a diameter into a circumference, you just multiply by pi. But the conversion issue became hard because we started with miles and we had to get down to inches. So that's number 37. I think I've got them all in now. So now I'm going to go to the beginning of the lesson. This is lesson 8.4. And the title is Area Measure and the Pythagorean Theorem. So let me just, I'm just going to explain this title graphic I have up here, just so you know what's going on there. The ancients could use a rope. If they had a couple stakes, they could use a rope to find a right angle. One way to do it is divide the rope into sections. As you can see here, I've got 4 sections from between the knots A and B. Then I've got 3 sections between knots B and C. And I've got 5 sections between knots C and D. And then if you just put each knot at a stake and stake it off so you have 3, 4, and bring the 5th back. So here's the 3, here's the 4, and here's the 5. Well, the ancients knew that when you have 3, 4, 5 triangle, there's got to be a right angle between the 3 and the 4. And you know why? Because of the Pythagorean theorem. Whenever you're in a right triangle, one leg squared plus the other leg, and by the way, legs are those things that make a right angle, plus the other leg squared equals the hypotenuse squared. And if you just calculate it, you can see that this really works. 25 really does equal 25. If that works in any triangle, guaranteed you will have a right angle between the two legs. So this graphic represents the second part of the title up there on the top, the Pythagorean theorem. I'm sure you've heard of that before. It's probably been a long time since you've seen that. Okay, then I'm going to talk about an area. As you can see, going back one more time to the title, the other part of the title is that we're going to be dealing with area measure. So addressing area, one of the most famous things to find the area of is a circle. And this little model, I think, is really an effective way to show that. So I know there's a little slice missing, but you can pretty much clearly see that we have a circle. It's in the first picture on the top left. That is what? Sliced up into kind of pieces of pie, if you will. And then in the second illustration to the right of it, you can see we've kind of pulled those pieces out and we're starting to straighten them out a little bit. And then down in this picture, you can see that after we've flattened them out a little bit, we can kind of shove them together. And then if you look at the bottom left, what we basically got is a rectangle. So just by creatively moving the pieces around a little bit, we kind of changed the circle into a rectangle. And now, keeping that in mind, look at this next slide. Oops. Look at this next slide. And I mean, how do you find the area of a rectangle? Length times width, right? Well, why did I call this longer side of the rectangle 1/2 C? Remember, that came from up here, right? Before we straightened it out. So that edge really was halfway around the circle, so it was half of a circumference. And what was this length right here? And here it is, right? Goes from here to here in the original picture. And sure enough, that was a radius. Okay. So length times width. Here they are. Well, what's another name for half a circumference? I mean, one way to write the circumference is 2 pi r. Or pi d, but I use 2 pi r, and I had to multiply it by a half because it's not a diameter. I said circumference. Yeah, circumference is pi d. But we only have a half a circumference, so I had to multiply it by a half. And what happens? The 2's cancel. And, oh my goodness. It's that famous formula, the area of a circle is pi times r times the radius squared. And what's, I think, kind of remarkable is after all these years, I had never really seen that shown as a rectangle. So in a way, if you creatively slice up a circle and reshape it as a rectangle, and then if you know a little bit about circumference, sure enough, we can find the area of a circle as if it was a rectangle. So, and the fact that I have this in a rectangle down here on the bottom, you probably know by now that means you need to know that formula. Okay, let's go. So anyway, I wanted to share that to you. We're going to learn a few, not a lot, but a few area formulas today. Okay, the next thing I want to show you, I'm jumping again to a different topic. We're going to talk about area, but I want to show you a principle of area. And what we've got here is two, I guess pizzas that are of different size, obviously. You can see that the one on the right is twice as tall as the one on the left. Twice as tall and twice as wide. I know you can't really make a pizza that's 2 centimeters in width, but only reason I laid the rule down is so you could see that one truly was twice as big. So this one over here is a 2 centimeter diameter. This one over here goes from 4 to 8. It's 4 centimeters. So we literally have what? Twice the diameter and twice the radius. Now you know that the area of a circle is pi r squared. We just went through that. Okay, so the one on the left, I guess let's just go with the one on the left. What's the radius? The radius of this circle on the left just goes from here to here. That would be a radius of 1. So it's pi times 1 squared. 1 squared is 1. Pi times 1 is pi. So when the radius is 1, the area is 1 pi. Okay. Now what happens on the right? We've got twice the radius, right? The diameter is 4, so the radius is 2. What happens when you do pi times 2 squared? Pi times 4. So here we got an area of pi square centimeters. Here we got an area of 4 pi square centimeters. So what happened to the area? It quadrupled. So when the radii were in a ratio of 1 to 2, the areas were in a ratio of 1 to 4. So, you know, if someone were to ask you, what do you need to do to double the area of a pizza? You don't want to double the radius, because if you do, you're going to get 4 times the pizza. So what's happening here is when you jump a dimension from a length, like a radius, and you jump to an area which is 2-dimensional, you always have that exponential change. Instead of 1 to 2, it's a ratio of 1 to 2 squared. 4. Almost nobody in real life ever remembers that, okay? And it's pretty important that you see it. In fact, if I push it a little bit further, here, let's just take another example. Let's say we had 2 objects whose radii were in a ratio of 2 to 3. Well, then, if we had an area made out of that, the ratio would be 2 squared to 3 squared. Why? Because we jumped up a dimension from length to area. So instead of a ratio of 2 to 3, it becomes a ratio of 4 to 9. And even though we haven't done it, if you went to volume, now you're jumping up 2 dimensions. Now you have to cube them. So instead of 2 to 3, it's now 2 cubed to 3 cubed, which would be 8 to 27. So whenever you jump up a dimension, you have to kind of jump up an exponent. So anyway, that may come up. I can't remember specifically in an assignment if it does or not. So then we come back to our right triangle. Remember how I showed you the fact that it's a 3, 4, 5 and it fits the Pythagorean theorem makes that a right triangle. So here are the area formulas I need you to know. And again, I've put them in boxes for you to remember. But before we can begin, I need you to look over here on the side. Whenever I use small b and small h, I'm using those to stand for base and height. And base and height, like I say right here in the middle of the page there, base and height are always perpendicular. They always form a right angle. In a rectangle, that's easy because the sides all form right angles. So if you look at the picture over here on the left, you'll see that B and H can be thought of as the sides because they make a right angle. How do you find the area of a rectangle? Just take base times height. Now, if you're wondering why I'm not using length times width, it's to make things a little easier for you as we move to the next step. And the next step is, what if we sit on a rectangle and I make it warp-like you see on the left here? We call that a parallelogram. And you notice the area formula hasn't changed a bit. It's still base times height. The difference is height is not on the side anymore, is it? Because height has to be perpendicular to the base. So you see I've drawn in a dashed line for the new height. And if you can figure out what that height is, it's the exact same formula as the rectangle. And then this goes even further. It's a nice analogy because now, what if we cut the parallelogram in half? What if we just snipped it right down the diagonal, the dashed line here? Well, isn't it just going to be half of the parallelogram? And it's exactly right. Notice the triangle formula is just half of the one above it. So far, 3 formulas, and I purposely saved you guys. You got 3 formulas, but 2 of them are identical. So rectangle, small b, small h, base times height. Parallelogram, base times height. Triangle, base times height, half of that. And then the one I showed you earlier is what? The circle. And in effect, that kind of comes from a rectangle. We're not going to go through that again. So I've given you 4 objects here: rectangle, parallelogram, triangle, circle. And there are only, what, three formulas. So the reason I used the BH, you probably see now, was to make it a little bit easier to remember. Okay. Now, this triangle, let's just go back one more time. Remember, the triangle is what? Base times height divided by 2. And I've got I don't know why I didn't draw it next to it, but down at the bottom here, I have a picture of a triangle. You must remember that B and H have to be perpendicular. So you've got to, you'll have to know what that perpendicular length is to have the height. So let's practice now. I have a sample problem coming up in this next slide. And here you can see my triangle is obtuse. That is, the solid line. There's the triangle. I should have drawn that maybe in a different color. But anyway, so hard for me to draw this exactly straight, but the red, that's the triangle we're trying to find the area of. Well, then how am I going to get base and height? I don't see anything perpendicular. And the answer is you can extend a side. You see how I made B longer coming out to the left here. And then I just went as far as the opposite vertex so I could put a perpendicular up there. Now I've got B and H. And if, let's say in this example, the base was 6 centimeters and the height was 8, of course we could just take base times height divided by 2. You can either multiply 6 times 8, get 48, 48 divided by 2 is 24. Or you could do some canceling, right? You could divide 2 into 6. Now you'd have 3 times 8, and you get 24 that way. Please note the label. Do you see how the label is square centimeters? That you can either write SQ period, CM period, or you can do centimeters with a little exponent for square. Labels, what I'm trying to get you in the habit of knowing is labels are important. So if I give you a label, then you should come back with a label in your answer. I'm just going to show this to you. You don't have to put this blue stuff down on the bottom, but really clever. I've always been intrigued by this. And if you don't know the base and the height, could you find the area of a triangle if all you knew were the 3 sides? And the answer is, thanks to Hero, yes. This is called Hero's formula. And if the sides of the triangle are A, B, and C, and then if you just add them up and cut that in half, that's called a semi-perimeter. This will work every time. It's really cool because then you don't need an altitude. So the formula is big square root, S again, semi-perimeter. A, B, and C are the 3 sides. S times S minus A times S minus B times S minus C. So you don't need to know this one. I don't know. It's a favorite formula, so I just thought I would share it with you. Okay? You really won't need it on any test questions or anything like that. Okay, so now some examples from the assignment. So you got to move, if you got your book handy, you want to move over to, well, it actually starts on the bottom of page 547, but the one I picked out, number 17, is from page 549. Maybe before we do that, let's just discuss some of the problems on the previous page, 548. If you have your book open, you see how we have some pretty exotic shapes over there. Like number 7 looks like a rectangle with kind of a triangle tacked on the left. How in the world are you going to find the area of that when all I gave you was the area formula for a triangle, a rectangle, a parallelogram, a circle? Well, isn't that just the area of the rectangle plus the area of the triangle? Yeah, so you just got to do that one in 2 parts. The I-beam, so to speak, in number 8, isn't that really just 3 rectangles? Yep. 9 is a half circle tacked on to a rectangle. So to find the half circle, you just, instead of using pi squared, just take half of pi r squared. So again, find the separate areas and then add them together. How about like 14? You've got kind of this ring. Well, you got a big circle and a little circle. Doesn't it make sense to find the area of the big circle and subtract the area of the little circle? So I gave you all the formulas you need to work on these problems. It's just that you got to be a little creative and either maybe use a little addition or subtraction to get to the final result. Okay, let's take a look at number 17. 17 says we have a rectangle that has a diagonal 17 feet long. Okay, I've sketched that for you here. Remember what a diagonal is? When you connect 2 non-consecutive vertices. Okay, and the length of the the length of the rectangle is 15 feet, which I wrote in. You are supposed to find the width. So I just temporarily called that W. And what's the key to our answer here? Because it is a right angle here, this we have a right triangle, and so we can and need to use the Pythagorean theorem. So one leg, W squared, plus the other leg, remember the legs are the 2 things that make the right angle, the other leg, 15 squared, equals the hypotenuse, that long side, 17 squared. And then you just got some arithmetic. 15 squared is 225. 17 squared is 289. Subtract 225 from both sides. And you're left with w squared equals 64. Then just to get w, we need to take the square root. And now we can see that the width of that rectangle had to be 8 feet, thanks to the Pythagorean theorem. So that's number 17 on our new lesson. I also want to take a look at number 22. 22, it says we have a telepole. That thing in the middle is my pole. I know that didn't help a whole lot, so let me get rid of that. Anyway, this vertical thing in the middle, make believe that's your telephone pole. And it's attached to points on the ground 15 feet. Let's see, supported by 2 cables attached to points on the pole 15 feet above the ground. So what they're telling you is this height right here is 15 feet. This vertical height is 15 feet. And to points on the ground 8 feet from the foot of the pole. So that's 8 feet, that's 8 feet. Okay, well, if it's a good telephone pole, it should be perpendicular to the ground, so you can make that assumption. You're supposed to find how much wire was used. You know, these are the 2 wires. These are the cables coming down on either side. Well, wouldn't that just be the hypotenuse of the triangle times 2? So 1 in the Pythagorean theorem, 1 leg squared plus the other leg squared equals what? I'll just say the wire squared. So 64 plus 225 equals w squared. That's 289. And then to find w, you got to take the square root. Turns out it's a nice even root. So now I know the length of the wire on each side is 17 feet. So how much wire did I need for the whole thing? 34 feet of wire. Hopefully that makes sense. So some of these are kind of like word problems where you really need to make a little sketch. Okay, I'm just trying to check messages here. And to complicate things, my cousin is sending me derogative messages about a non-Green Bay Packer football team. I won't say who it is, but the first name, their nickname begins with a V. Anyway, I'm sorry about being interrupted here. So I'm just checking again. Yeah, I guess nothing new from you guys. Okay, so next I would like to take a look at number 30 on the assignment. Number 30. This is a little different because this time they give us the area. It says, you know, one of those Guinness Book of Records relates to what's the biggest pizza? Whoops. What's the biggest pizza? And I'm sorry, I'm trying to get this thing so I don't, anyway, never mind. So they tell us the area of a pizza is 5,024 square feet. What is its diameter? Okay, so by the way, they didn't say it, but they're assuming this is a circular pizza. And so the area has to come from the area formula for a circle. So the first thing you do is write down what is the area of a circle. Pi r squared equals what they told us, 5,024. we're supposed to find the diameter. Well, to find the diameter, if we could find the radius, all we'd have to do is double it, right? So how can we find r? Well, we kind of need to get pi out of there. We can do that because it's being multiplied. We can divide both sides by pi. Okay, so now it looks like this. The pi's cancel on the left. We got r squared equals 5,024 divided by pi. And then we got to get the r, so we got to take the square root. Sorry. We got to take the square root. And then we got the radius. But we have to double that, don't we? So here's where I went to the calculator, and I did 5,024 divided by pi. And then I found the square root of that, and that turned out to be just about exactly 40 feet. And then when you double it, the diameter has to be 80 feet. So here's a case where we had to start with an area formula and work our backwards in order to find r and at the very end, d. Next one I would like to show you is number 32. Again, a little bit different. So number 32 says, find the height of a triangle of area 70 square inches if its base is 20 inches long. So hopefully it does, see if my picture makes sense to you. First of all, I wrote down area equals 70 square inches. Then I sketched a triangle with a base of 20 inches, and then I sketched in the perpendicular height that goes to the vertex. And that's what we don't know. So h is what we're trying to find. So which formula do we need here? The area formula for a triangle. Do you remember that from a little bit earlier? That's BH over 2. Base times height divided by 2. Well, I don't know h, so that's okay. Plug in, here, let me undo the blue here. That's kind of from another step. Forget about that cross out. So base 20 times height. Right now, all we know is it's h divided by 2. How can I solve for h? Well, one thing I could do, and this is what you saw a few seconds ago, is can't I get rid of that? What I probably should have done is just cancel. What's 20 over 2? 10. So this is really just what? 10h. And then, to go the next step, coming down here in blue, you've got 70 equals 10h. Can't I just divide both sides by 10? Yep. So now we can see that the height, this is supposed to be an h here. Sorry, not very clear. The height has to be 7 inches. Okay. Another one? No, I got. So here's the assignment I normally give in class. I'm going to cut that in half again for you guys. So instead of 1 to 43 odds, I will again assign you guys the every other odd. So 1, 5, 9, 13. You get the idea. And you don't have to go past 43. So now I'm going to tell you right now, don't get too hung up on number 43. It's kind of a beast. Try working on it, but I'll work on it in class, okay? 43, and there's another one that's really a stinker. And I don't know if it's on your list of every other odd or not, but it's the, let me find it. I'm not finding it right now. Anyway, if you come to any real stinkers, don't get too upset. Try working on them, and we'll start off Wednesday night session looking at those. They should be good learning experiences, but that problem example of a problem that's really too hard. Okay, so 43 is, I don't even know if it's on your every other odd list, but too hard, but it's a good learning, it's a good problem to work on. Oh, I know, another one is number 37. So 37 and 43 are, you know, they would definitely be like extra credit problems if they were on a test. Okay. Yeah, those are the two I wanted to point out to you. And I'd still like to work them through with you, but so don't sit there and tear your hair out working on those two, but see what you can do to get started on them and see how far you can get. All right. Are there questions you would like to send my way? Alan, I hope the coffee was good in the coffee house where you were. Everybody else, I hope you have a good rest of your Sunday. Thank you for tuning in, and I look forward to seeing you guys on Wednesday. Send me your questions if you'd like.